On December 12, 1984, the United States Air Force and NASA began testing an unusual aircraft, one that broke all aircraft design convention. Its wings pointed forward. However, this experimental aircraft, dubbed the X-29, was not the first of its kind. The Germans also experimented with the concept in the late stages of World War II with the Junker Ju-287, and its prototype airframes would eventually end up in the hands of the Soviets, who took and developed the design into the OKB-1 EF-131 and the OKB-1 140. All of these early iteration designs ran into the same problems. This design was incredibly aerodynamically unstable. When the wing deflects, the force of the oncoming wind tends to make it deflect even more. This is a rather obvious design flaw. Intuitively, you know just looking at it that something doesn't quite make sense. So, why did Germany, the Soviet Union, and the United States all see the design worthy for consideration? To understand this, we first have to explore why wings are swept beyond a perfectly perpendicular angle in the first place. Looking at most aircraft developed during World War II, you can see that nearly all of them had straight wings. The Spitfire, the Mitsubishi A6M0, and the P-51 Mustang. It was only during the later stages of the war, as more powerful engines came to the fore, that other designs started to emerge. And in one case, the straight wing became a major design flaw that put the crew of the P-38 Lightning in serious danger. These problems arose directly as a consequence of how wings generate lift. An aerofoil is designed to make use of Bernoulli's principle, where a low-pressure zone is created on top of the wing as a result of airflow moving faster. People like to say this is false, but it's just one of the ways a wing generates lift. There is a lot more to the story. Because this airflow actually speeds up as it crosses the wing, it can reach supersonic speeds long before the plane itself reaches supersonic speeds. This causes problems because supersonic flow means shockwaves form, which can disrupt normal airflow over the wing. On November 4th, 1941, these problems resulted in the death of Ralph Verdun, an expert test pilot, during a high-speed test dive of the P-38 Lightning. The causes of the crash were unclear at the time. This version of the P-38 had been altered with superior servos for the control surfaces to help the pilot overcome aerodynamic stiffening, where the force of oncoming air at high speeds makes it difficult to move the control surfaces, but the plane still entered an uncontrolled dive regardless of these measures. The engineers eventually discovered the airflow was separating from the surface of the wing as a result of shockwave formation. This reduced the lift the wing could generate while increasing the lift on the tail wing directly downstream of the flow separation. This moved the center of pressure and forced the plane to pitch downwards and gain even more speed, making it next to impossible to recover from. To solve this issue, they incorporated a dive flap on the lower surface of the wing where airflow was not reaching supersonic speeds, which could be deployed during high-speed dives to allow the wing to generate lift and recover from the dive. As technology advanced, however, aeronautical engineers started to see that straight wings were not suitable for transonic and supersonic speeds and gradually started to adopt swept wings. The Germans confirmed the theory with high-speed wind tunnel testing in 1939 by testing two wings, a straight wing and a swept wing with a 45-degree sweep, proving that a swept wing would delay the onset of supersonic flow and reduce drag. They recognized that the swept wing would allow a plane to fly faster before shockwaves formed, long before the technology that would enable them to fly faster was even invented. They used this knowledge to develop the Messerschmitt P1101, a jet-powered plane that could actually change its sweep angle before flight. But the end of the war came before the Germans could finish it and test the aircraft, and it was captured and developed into the Bell X-5 by the United States. To understand the purpose of sweep angle, let's see how airflow evolves over this plane's wing as it changes its sweep angle while comparing flow over a straight wing. Airflow over a wing perpendicular to the free stream air has one component, the chordwise flow, which is the air that flows over the chord of the aerofoil. The chord is the imaginary line running from the leading edge to the trailing edge of the aerofoil. Chordwise flow does accelerate over the aerofoil and thus contributes to lowering the speed at which supersonic flow begins, called the critical Mach number. Now, let's look at the flow components over the Bell X-5's wing at its lowest sweep angle, 20 degrees. Here we can separate the airflow into two components, the chordwise flow, which is now offset at a 20-degree angle relative to the free stream, and the new second component, the spanwise flow, which flows along the length of the wing and does not accelerate, and thus does not lower the critical Mach number. At lower speeds, where supersonic airflow is not a worry, you want as much of that airflow to be chordwise and thus generate the necessary lift to fly. However, as the speed of the plane begins to climb, we are generating more than enough lift thanks to the increased airspeed, and thus can afford to convert some of that airflow into spanwise flow. We do this by increasing the sweep angle, which the Bell X5 could do in flight to a maximum sweep angle of 60 degrees. As the sweep angle increases, a larger portion of that airflow is converted to spanwise flow, which is great for increasing the top speed of an aircraft but can cause some troublesome stall characteristics. Because a large volume of air is now originating at the root of the wing and travelling down to the tip of the wing, stall will begin at the tip of the wing and move towards the root. This is a problem because our ailerons, the control surfaces that allow us to roll the plane, are located on the outer wing. If stall occurs on the outer wing, we lose roll control. A major problem for, say, a fighter jet attempting a high angle of attack maneuver while maintaining full control. And this is one of the problems forward-swept wings were trying to fix. This reverses the direction of the chordwise flow, so it originates at the wingtips and travels to the root of the wing, meaning stall occurs at the root of the wing first, allowing us to maintain control of the plane for much longer. Not only that, it also reduced induced drag as a result of wingtip vortices, where high-pressure air from the lower wing travels and mixes with low-pressure air on top of the wing at the wingtips. The Ju-287 was designed this way not to benefit from the superior aerodynamic characteristics, but to move the wing box rearwards, which allowed the bomb bay to move forward closer to the center of gravity of the aircraft, which in turn allowed the plane to carry a larger bomb while not increasing the trim drag to keep the plane balanced. But ultimately, the materials at the time could not facilitate it. Under normal wing loading, the main force being exerted on the wing is upwards bending, where the force of lift pushes the wing upwards while the weight of the fuselage pushes downwards. To survive this, we need to build an adequately strong and stiff wing. This is achieved through a beam called a spar, which runs the length of the wing. With a forward-swept wing, an additional stress is introduced where the force of oncoming air is attempting to twist the wing. We can imagine this with a free body diagram, with the springs representing the stiffness we need to incorporate into the wing. Here, Kb is the spring stiffness that will be needed to resist bending, and Kt is the spring stiffness needed to resist twisting. Creating a structural member that can act like this torsion spring over the entire wing, however, is no easy task and would require enough additional weight to negate any positive attributes the forward-swept wing would provide. But that changed when advanced composite materials became available, allowing planes like the X-29 and the Russian equivalent, the Su-47, to be made. Both planes use carbon fiber reinforced plastics laid up so the fibers would resist that twisting motion. I will focus on the X-29 from here, as information on American technology is far more freely available. The X-29's primary structural member for resisting this twist was a closed box section located here, which was constructed of crisscrossed composite tape that reached up to 156 layers deep, essentially creating that spiral spring shape within the structural member, but with extremely stiff and lightweight composites, taming that twisting motion and allowing the plane to fly successfully. Wind tunnel tests show that the forward-swept design would provide a 20% gain in efficiency compared to the same plane with aft-swept wings. This, along with a supercritical wing design, which flattens the top edge of the aerofoil to minimize the acceleration of air over the top edge, while introducing a concave curve to the lower surface to increase lift, allowed the X-29 to spend less fuel flying at a higher Mach number. Another drag-reducing benefit of the forward-swept wing was the shifting of the center of pressure rearwards. Typically, the lift generated by an aft-swept wing needs to be counteracted by a tail wing, which generates downwards pressure to maintain pitch stability. This downwards pressure is wasted energy that contributes to drag. With a forward-swept wing, the center of pressure is moved to the rear of the aircraft behind the center of gravity, and thus to maintain static pitch control, These pitch control surfaces, called canards, need to generate lift forward of the center of gravity and thus contribute to useful lift. This would seem like an obvious feature to incorporate into every aircraft, but leads to instability that requires the control surfaces to constantly adjust to maintain stable flight, and this was one of the massive challenges the designers faced. The X-29 was incredibly unstable, especially in pitch, even when compared to modern jet fighters. This means the flight control computers had to be constantly adjusting the control surfaces to maintain stable flight, about 40 times a second. To do this, the X-29 had 3 flight control computers to provide redundancy if one failed, as the plane would become essentially impossible to fly without the aid of a computer, which made it even more worrying when all 3 shut down while preparing to take off. This caused the plane to be grounded, delaying testing, which was due to accelerate with the arrival of a second X-29, fitted with a parachute system to allow high angle of attack maneuvers to be safely tested. The spin parachute was installed to provide positive recovery from spins, as wind tunnel tests had indicated that the X-29 ailerons and rudder provided poor recovery from fully developed upright spins. Eventually, the problems were solved and high angle of attack testing resumed and proved the X-29's capabilities, but the program ultimately ended on December 8, 1988, almost 4 years to the day of its first flight. In between that first and last flight, the X-29 completed 242 flights, with 179 combined flight hours, providing valuable scientific data and design experience in composite airframes and computer-aided flight. Ultimately, forward-swept wings weren't incorporated into newer generations of planes, as the benefits simply did not outweigh the cons, from the additional structural requirements, the poor pitch stability, and perhaps most importantly, its negative effects on stealth design. In the end, aft-swept delta wings won out.